All right, let's get going. We have a lot to go through, so I'll try to get as far as I can. Yeah, so let's talk about using WebAssembly components to build next-gen architectures. One thing, we had a last-minute change to do it in English instead of in Dutch. I hope there is no big problem for anybody for that. But with that, let's get going. So it is a big subject. There's a lot of stuff to go through. I am trying to get enough of the basics of WebAssembly in there to make the whole story make sense. There will be some gaps here and there, but yeah, there's a lot to go through. So I hope this is enough to inspire to look into that more. So first of all, about me, I'm Frank. I'm a senior cloud engineer for a long time. I've done pretty much anything on the dev side. Right now, I'm working at HighTech Innovators in the sustainability team, and that's also one thing place where WebAssembly is interesting. I occasionally stream some Rust programming online, and yeah, I love speaking out on subjects that interest me. So, uh, one thing I want to talk about is the word cloud native, because that's something we throw around a lot, and we kind of seem to know what it means, but nobody really boils down to it. But if I look around, it pretty much always means something like things with Kubernetes. And I guess that's the case, but I want to put some question marks here and there. What is exactly cloud native about that? Is it, yeah, what parts are cloud native? So what Kubernetes does is basically run containers and do stuff around that, but the thing it does is running containers. So for me, the next question is a container cloud native? Uh, kind of, but also not really, right? Because if you ever look inside a container, so in this example, I ran just a simple Ubuntu container and I look inside of it, and it seems oddly familiar in the sense there is stuff in there that you think, why is it there? Like there is a dev folder, that means in Linux that there are devices. There are no devices, it's a container, there is nothing there. The slash proc maps to processor and processes inside machine, but also it's kind of fake because it's not really there. It's like a mapped from the host in some way. There's even a home folder for users. There are no users. Like it is a weird kind of time capsule from when it was still a real computer. It's kind of a cosplay of this is a computer, even though no most of it isn't really there. So over time it's gotten less. There is like most applications don't need anything anymore, but it is kind of a sign like this is what apparently is necessary, right? Because in the an application needs something like a container to be cloud native. So in my view, like a container is like a suit. Like an application in itself in its raw form would not do well in the cloud, and that's why we have containers. So in that sense, is a container cloud native? Well, kind of the outside is and the inside isn't. Uh, so if we follow that reasoning, and if we need a spacesuit, why wouldn't our application do well in the cloud? Why aren't we cloud native? And that goes back to a very ancient API we all use, and that API is called POSIX, and it's I think about 50 years old, maybe a little bit less, but something like that. So it's really old. It's a C API, and that's the API we use to do stuff. Like pretty much anything a process does on the machine is in POSIX. So you can, yeah, as you see there, you can access other processes, you can access file system, networks, timers, all the things that programs do. Um, and that's a really one size fits all API. Uh, and even though the operating system can have some permission structure of what you actually can do, but in principle, you can do all those things. And Windows is a little bit different, but like it's a different system, but it's the same point, right? It behaves in the same way. So we call this allow by default. If you have a process, you run it, this is what it can do, unless you somehow restrict it. And that's important. And we call that notion allow by default, right? We are responsible of making sure it doesn't do anything we don't want it to do. What stack we use doesn't matter at all. Anything uses POSIX, Node.js, Java, Rust, everything in the end comes down to the same API. So tech stack doesn't matter. Let's take an example, right? If we have the most basic command in Linux, the ls command that lists files in a folder, it has POSIX access. It can do all of these things. Like if you think about it, well, it obviously needs access to the file system. But aside from that, does it need to spawn other processes? Does it need to open sockets? Because it is a bit of a liability in a sense. Like the ls command could reach out to some server in a hostile country, download a binary and run it. Like it can do it. The operating system might prevent it or some other malware prevention, but you're never sure in a sense. So that allow by default is a liability. We would prefer to have something like this, right? That we really exactly choose what we want to share with the world. Uh, in this case, like there are no pointer sockets, it doesn't need to see other processes, just want to look at the file system. Maybe timers that you can show how old the file is compared to now, but yeah, not a lot. And that you can see that on the outside, this is what it can do. And but we are kind of used to it. Like this is the way it is for a long time. So yeah, that's where we are. So that's why we kind of need containers because we don't trust our own software. For that, we get the wisdom we all have as backend engineers that we should not run untrusted code, that we should know what we are running. And that its value is obvious, but it's also kind of useless because we do it all the time in some sense. Especially, for example, cloud providers. Like that's their job. You give them a bit of money, you give them some code, and even though they barely know you, they will run it. And they get away with that because if you give them their binary, they'll put it in all kinds of containers, VMs, both, right? So they will wrap it up tightly because that application is not cloud native. So that's one side of the story. Uh, Another side of the story is if you have an application like, yeah, it doesn't matter what it is. You have some server, you have some clients, you have some database. All the traffic goes through the same memory space, right? So that those different users can be getting and retrieving data from the database, and you don't want one user to see another user's data. Well, that's our job, right? To get that right. We've been doing that for a long time, but there is no guarantee there, and not just for our program, but also for all our dependencies. Like it would be very bad for especially if you have memory unsafe languages. So, for example, if we would run it in C, a simple buffer overflow so that you can just basically see the entire memory space, that would be a big deal. It's a little bit better on higher level languages if you use something like Java or Go or C Sharp, where you virtualize away the memory space at least so that you just can't run around. But still, like if you can get access to the whole virtual machine, it still contains sensitive data. And because it also includes all our dependencies, we have to not trust our own code, but every code that the whole transitive dependency tree runs on. And there have been many cases that some edge library that everybody uses but nobody cares about has a vulnerability, which end up being a big deal, and then we all have to scramble and update our application. So I think right now we are not cloud native. I think we have a lot of work to do, and hopefully we can somehow see if perhaps WebAssembly can work. So these are the two security problems I have discussed. The single memory space I just talked about, and also the monolithic ABI. That means that you kind of have an all or nothing kind of access to the system, and nothing is kind of useless, so all it is. With that in mind, let's get into WebAssembly. I'll just go through a very brief and yeah, hopefully concise memory history. Let's go. It was conceived in 2012, so that's a while ago, and it was started as a subset of JavaScript. Um, JavaScript is not great at everything. It is used for everything, but if you want to use a lot of computational intensive code, it is not very performant. Let's see. I have. Oh, there are some new ones. Yeah, sorry. I had to admit some people. It was a subset of Java that would make that performance a whole lot better. And that kind of worked. And if you have been around for since that time, then all of a sudden you could run Doom in the browser, and that was really cool. There was a nice progress there, but it was a kind of impossible programming model in a sense, like something that's nearly JavaScript, but you can't really do the JavaScript things. So it was kind of redesigned in 2016 by the bytecode it was basically shared between a lot of browser vendors. They all worked together surprisingly well, I think, to get it out there, and now it is pretty universally supported. It's a binary format, so it's not like JavaScript that you actually ship source code, you ship the binary. Stack-based computer, so it's not like you're setting or getting registers, you just put everything on the stack. And it's a compilation target, meaning that no sane person would really want to write it manually. You compile some language to it. What does it look like? Well, you don't really need to look at it. This is adding two numbers, so that kind of tells the story why you don't really want to look at it. It's a lot of stuff, so it always ends up being a module. That's kind of the unit of code of WebAssembly. The double semicolons is a command line, and then we have one function that ends up taking two parameters, putting them on the stack, calling the add operator, and then the result will be on top of the stack, and that's what will be returned. But that's enough about that. Like there is a lot more there, obviously, but that doesn't really matter for now. On the client side, there was quite a bit of adoption on the sort of high-profile cases. Like Photoshop had an interesting case because they wanted to move from a desktop to a web-based product in Photoshop. It was a very old code base in C++, so they didn't want to port it to JavaScript and at the same time be on the hook to maintain both of them in parallel. So they used the fact that you can compile C++ to WebAssembly to create a web version on a single code base. Figma is like a shared whiteboarding tool. I haven't used it much. But it's more of a tool. The use of WebAssembly is more about the improved performance of the client, so you can do very nice visuals that you wouldn't be able to pull off in JavaScript. DuckDB is a database. Well, kind of. It is an analytics database. It's not like a server database that you run. It's more a command line thing, and that you can basically run that against some file or some URL, and then you can run analytics on it. And the fact that you can compile it to WebAssembly now is basically you can put it on the website itself. You can share a link to someone, and you can let someone do analytics on the fly on their own hardware, which is really cool. And also it works nicely with WebGL, which is kind of GPU access for graphics from JavaScript. So yeah, this enabled a lot of use cases that weren't really possible before to run inside the browser, and now they are. So, and so the requirements to get there, you need high performance, right? None of these things would work if it would be a big performance hit. The web is a very hostile place. Yeah, we talk about not running untrusted code. Well, in a web browser, we do that literally all the time, right? So it downloads code from somewhere on the internet and then it runs on your own machine. So the sandboxing needs to be really strong. And this is one of the cases also in JavaScript, is that there we don't have positive access for very obvious reasons. Finally, lightweight. Binary size matters for web usage. We don't want to download a gigabyte of a container or something like that. So it is always a point of attention, and also it needs to load quickly, right? And that's advantage of being a binary. It loads much quicker than, for example, JavaScript. JavaScript takes some time to parse, and once it starts up, because it's a kind of JIT virtual machine, it needs to warm up a little bit. It will run badly for a while and then it gets better. The binary format of WebAssembly will run just immediately on its max performance. So these properties also got interest of backend developers. They think like me, like I think I want some high performance build for untrusted code, lightweight stuff as well. And that has been going on for a while as well, so that we can run WebAssembly outside the browser. The best known implementation of a runtime is wasmTime, is by a sort of a reference implementation, so that tends to have all the features. Wasmer, I don't know that well. It's an alternative implementation. And finally, there's Whammer. That's a very minimal implementation meant for embedded components. So running on microcontrollers like ESP32s. So you can run if you want very tiny modifications on, for example, some smart device, then WebAssembly can be nice to isolate that, because if you would allow real access, then if you get it wrong, you break the whole device. So let's look at the server-side example. This is a microservice. I'm a little bit in front of one of them. Doesn't matter. It's based on a Quarkus demo. The people who know what I've been doing have seen this before, probably. It's a microservice with some services. They all have a database, and there's one. It's a service that gets superheroes and villains, and they fight them in a certain location and stores the result. That's what it does. What's interesting is it receives HTTP call and it calls some of the backend service, if that makes sense to you. Let's zoom into one of those services. Like this, it has a HTTP REST endpoint, and it has some runtime, and it has a data store, right? Could be anything, could be all kind of runtime, doesn't matter. If we zoom in a little bit more, then we also see that that runtime has a bunch of dependencies, right? You need to parse JSON, you need to parse HTTP. If you want to write in log files, you need to include a log library. You need a drive for the database. So there's actually quite a lot of stuff in there, even though the code in it might be very simple. So we could replace this runtime with a WebAssembly runtime. So if I do that, or watch closely, now it's a wasmTime runtime. Nothing changed. That does work, and that's kind of the first generation of server-side WebAssembly. It was called WASI P1. I'll get back to that. So it's kind of a monolithic replacement of a runtime. What is the point? Well, one thing that Wasm does very nicely is the lightweight part. Running this service, it can start so quickly. sub-millisecond, that you don't need to keep it running. So whenever there's a HTTP request, we just spin up this whole system, and it processes the request and then closes it down. So that has a few really nice properties. For one, we have that separation of memory space. If you have two requests, they don't have any memory space they share because they're kind of like different processes. Mind you, they're not actually different processes. This is like inside the single process, the runtime has different memory spaces. Also, we don't need to keep it running. So if we have an application that has one call a month, like it does that call, but outside that, it doesn't use any resources, which is also nice because it kind of makes the cost of microservices just to have it a whole lot lower. So yeah, it does not solve all the problems we were talking about, because right now, if we look at like the POSIX thing, the permissions, is that we need to give one blanket access to all the parts of this runtime. So for example, if we think about it, if we have a log that writes to the file system, then that log needs access to the file system. HTTP needs to receive incoming requests from the network. The database driver needs to be able to make outgoing network connections. So in a sense, if we put that all together, we end up with that any application of any kind of complexity will have all the POSIX things anyway, right? Because we have to, they're all living in the same module. So can we do better? Yes, we can. And that's called the WebAssembly component model. And that's, it started when WebAssembly started to gain some traction on the server side. And it is a model to organize code in a more reusable fashion. So the component model, if you are familiar with OSGI in the Java space from way back, that might ring a bell. But it's a model where for every component you can declare what it needs, what external service it needs to operate, and what services it offers. And if you have a bunch of those components, then they can resolve each other, and then hopefully every component has what it is, and then it can expose what it needs to do. It's polyglot, so it can be any language that can compile to WebAssembly. And from the outside of the component, you can't even tell. They are basically indistinguishable in the sense that you can't really tell which language it's programmed in. But to do that, you need some way of expressing those requirements and the service it offers. There's a special language for that. I'm not going to explain it totally, but you kind of figure out when you see it. And it is called WIT, W-I-T. And that's sort of manifest that you attach to every component. So here you see, for example, the world that means like the component in itself. And you see is two imports, so that's its stuff it needs to do its job. So this would be one of those services we were looking at. It needs a database access, so that's the Postgres query import. So declaring that means that you can use the functions in that module. It also needs to handle incoming HTTP for the types, and it also exports the incoming HTTP. So it says like, when I am ready to go, when all my requirements are met, I can handle HTTP requests. So that's kind of in a nutshell what the WIT definition is. And this is about the the system interface, because what we were talking about before, like in the sense that POSIX is a one size fits all kind of compute operation in one API. If you want to run server-side compute, you need some access to the operating system. Otherwise, it's useless. But on the other hand, you don't, to be able to trust untrusted code, in a sense, you do need to sandbox that. So the interface that's basically WASM's answer to POSIX is called WASI, WebAssembly System Interface. And the first iteration, called P1, was basically POSIX ported to WebAssembly. And that was kind of nice in the sense that it meant that you could pretty easily compile an existing application to WebAssembly. But it kind of retained all the problems we had with POSIX, because you can't do anything. It's up to you to make sure nothing escapes. And the current version, P2, is based on the component model. So now we have to really declare, like I just did in the WASI file, if I want to touch anything outside this component, it needs to be there. There is the P3 version will be released this year. That will include async and streams. That will make the performance quite a bit better. And hopefully in 2026 there will be a 1.0, so there is a little bit less breakage. And there are also some other work in progress, like threads and garbage collection. I might mention them later. Let's continue. So if we look at the component, it looks something like this. So we have our code, and we have the APIs it declared, right? So we have, in this case, we had the log API we imported. Did we import it? No, we didn't import. There was a different one. Never mind that one. We have the HTTP API we imported, and the SQL API that we imported as well. But that's just it, right? It's an important difference to notice that the database driver is not inside the component. The log driver is not inside the component, nor is the HTTP API. It just shows like there was an HTTP API, this is what it looked like, but the parsing is not in there, the drivers are not in there, and that's a really nice advantage to have, rather than just putting everything inside, because then you have the vulnerabilities, right? So now, if you have a problem with your SQL driver because there's a vulnerability there, it can't reach your process because it's in a different space. I won't stick around here long. This is an implementation of one of the services that basically handles a request. It's Rust code, but you can. It is pretty familiar. If you've seen one, you've seen them all in a sense. But you can see that there are no imports or use in this case of the standard library, because it's not there. You can't use the standard library here. You can't spawn threads. You can't do any of that, and that's an important reason. You also can't use the file system. It's not just that you don't have permission to ask the file system. This piece of code doesn't know what the file system is. So that's an extra level of protection because it's just not there. We have created an API to query a database. So in that sense, it is not the most impressive thing, but we have touched on some important things. We scale to 0. So we don't need to have a process hanging around just sitting there when there's no traffic. We have polyglot components, so we have different components in different languages. They all seamlessly work together. You don't even need to know. Every component only has the permissions it needs. And now, if somebody offers another component with a capability, we can pretty safely include that in our stack. A lot more so than when we would not have this sandboxing. We can take it one step further. So back to this one, we have those different services. They used to have different processes where they would call another. If I would, in our port to WebAssembly now, it looks something like this. They all run inside a wasmCloud cluster. wasmCloud, yeah, I have no time to get into it. It's kind of a Kubernetes for WebAssembly. But now they all run inside that cluster, but they still do those REST calls, right? So the fights one that calls all the other ones. So if we look at the WIT file for the fights, that looks like this. It's pretty similar to the other one. It has logging, it has the incoming handler because it needs to accept HTTP calls, but it also makes outgoing calls. So that's a different API. It's not necessarily the same. So we are still making network hops. And we can make the argument that maybe we don't need to make all those network hops. Maybe we can do something like this, that we create a special API from the services, and we can use the component model to assemble them together. So if we would implement that idea, it would look something like this. So if we have a place where we can query the heroes, which was a HTTP JSON service before, we can say we make an interface. This is a WIT file, and we have some functions like get hero, get all heroes, and we define what a hero is, and then we define this whole thing as a component. If we do that, we can actually prevent that network hop between those two services. Because in terms of sustainability and efficiency, network hops are super expensive. You need to take all your data, you encode it in some JSON, and then you send it all the way through all the stacks. You probably encrypt it once or twice on the way, and on the other side, you go back up until you have your data again. And for simple requests, it can easily be 1,000-fold slower than a local service call. So in this case, there is no real reason for the network hop. It's mostly because we're kind of used to it for microservices, right? In a microservice, we have said, well, we don't want to mix code together, so any component that talks to another component needs to do so through a network socket. Is that still a microservice if we do that? I don't know. It is something that we might need to think about. It's something to think about. Maybe in some cases it is, sometimes cases it isn't. But we do need to realize how expensive network hops are. This part I'm gonna skip because I'm running out of time. So wrapping up, I think scale to zero is a very powerful thing, also in terms of sustainability. Like, just we have so much stuff running on a lot of hardware that is scaled to have enough capacity for the peak. That is just doing nothing most of the time. Uh, uh, and yeah, there are some other places where WASM is interesting. Also for streaming data. Red Panda is a sort of Kafka. That's nice. There's a stream processing framework, Fluvio, that does nice things. It's similar to Apache Flink, if you know it, but also much more lightweight. Back in the Sur Spacetime DB, I had to skip on that. It's really cool. Maybe for a follow-up, but didn't have time today. CDNs, so something like Fastly, where you have edge computing in a sense that if you want to do a little bit of processing there, then WebAssembly is really nice because a container would be just too heavy. It's not all great. It is bleeding edge. There is a lot of stuff out there that just barely works, or that used to work, but now there was a change, so it doesn't work anymore. So you need to be a little bit confident to reach out to the communities and talk to them. However, the communities are really very open and friendly. That's, I think, always the nice part of being on the frontier, in the sense that if you want to ask a question to the wasmCloud folks, you'll get very good answers from very senior people really quickly. If you reach out to the Spring Boot team or something, you can forget about it. Like it's just a different world. Other challenge, debugging is a bit rough right now. It is a fundamentally difficult thing because it's polyglot, right? If you have a service combined of different components in different languages, you could theoretically step through them from one language into the other and back. But none of the language tool change really thought of that. So it is not quite there. There is no reason it is impossible to make this well, but it is yeah, it does take some work. The polyglot programming model, yeah, there's a lot of things that work better in one language versus the other, and also the width definition is really close to how Rust works, for example. So in Rust it feels fine. In other language it just feels a little bit off, and that's like the price of polyglot, right? There is some gray areas where it doesn't all fits nicely, and yeah, it's about changing stuff that hasn't changed in a long time. So that does require some rethinking. Uh, Finally, a few more minutes. Uh, it's just adding WebAssembly to your stack and not removing anything only gets you so far. Like it's not about just having your stack sprinkle some WebAssembly on it and then things will be great. No, you need to do that, but also to see what it enables you to do and what kind of uh, decisions it allows you to rethink. Because now you can trust code, untrusted code, or you don't need to do that network hop. So it does have on the tail end a lot of extra benefits, I think. So that's pretty much all I have for today. I think this can take us to the cloud without using any containers, and that's all for me. So if you have any questions, please ask them in the chat. I have a few on different chats. I have one question: which programming languages can be compiled to WASM at this moment? Well, theoretically, all of them. But because like there is a GCC can just target it, and if you can somehow supply all the libraries something needs, you can do it. However, you do need to include the runtime then, and that's the kicker mostly. For example, if you want to run Java and WebAssembly, that would require you to run the JVM in WebAssembly as well, and that's a big thing. And if you then you will end up with such a big WebAssembly component that it might cancel out any advantages you had. So it might not be worth it. However, there are some initiatives like before I skipped over it mostly, but wasmGC. That's an extension of WASM that basically uh, offers a garbage collection to WASM, so you can have a garbage collection outside of WASM that just you can use from the module. So that would make the whole, for example, Java environment a lot lighter. Languages like Python that are basically interpreted, they work, but again, the interpreter needs to live in WASM. It works, but it is heavier. And yeah, there are some. So mostly the lower level languages, the Rust, the C, C++, Go. to an extent. They work nicely. The higher level they get, the more painful it gets. There are a few like Grain that are kind of esoteric, but they are WebAssembly only, which is also cool. I hope that answers your question. Next question. We have if we want to use WIT to define our components, don't we need tooling to convert WIT interface definitions to whatever language we want to implement the consuming component in? Yes, you do. And that will be different from every language ecosystem. There is for Rust, for example, there's with bindgen that's pretty mature because yeah, there is a very lot of Rust in this area. Go is also pretty good, but yeah, you need to make something that feels nice in the environment. And for example, like it uses result types like Go does or Rust does, but in Java you might expect an exception or something, and maybe you can model that. But yeah, the maturity really depends on the language stack. Are there any other questions? Someone's typing. All right. So yeah, there's one more here, and that's oh, there's recommendations for IDE. It doesn't really, well, it's mostly around your language preference. So whatever works. I don't think it matters much if you compile to native or to WebAssembly. I use VS Code for Rust mostly. Occasionally Z as well, which is a nice IDE for specifically Rust. But yeah, I don't think it matters whatever you're comfortable with. All right, if there are no more questions, I want to thank you all and see you all around. Reach out to us at the HighTech Innovators if you have questions, or to me on LinkedIn, other channels, and hope to see you around. Thank you. Bye bye.